All right, let's look at sample test 5 for physics 244. All right, hopefully we can see everything there. All right, when an electron and hydrogen atom moves from the ground state to the n equal 4 state, the atom must, so the ground state is the lowest, n equals 1 state, and we're going up to the n equals 4. So it's going to take more energy to be out there. The n equal 1 is the lowest energy. So to go up there, it has to get more energy, so it has to absorb energy. Right, when it goes up, it has to take in energy. When it comes down, it gives off energy. All right, what color of light would release electrons from fewer types of metals? So the photon energy is hc over lambda is one equation, and so if lambda is bigger, then we have the energy goes down, right? So then it means fewer metals. All right, so from the fewer types of metals, we want the one with the highest wavelength. Yes, highest wavelength, lower energy, fewer metals. So of the colors, remember lambda has the highest, red has the highest, and then, yeah, kind of in this order, and then green, and then blue, and then violet. Lambda. Lambda blue. Lambda violet. And so the one with the biggest wavelengths then is red. Right, if you remember, we have our equation sheet from last time. If you forget, looking at the wavelengths, lambda for red was around 700 nanometers, whereas blue or violet is actually 400, and so red has the biggest wavelength. Okay, so that is A. Which H atom would be the largest? Okay, so for size has to do with if the electron is in the close-in energy level, it's smaller, but the higher N is, the further out, the bigger the shell that the electron is in. So ground state, N equals 1, that's the smallest it can be. Second excited, that's N equals 3. Because this is the first one. The first excited one is 2, the next excited is 3, N equals 2. All H atoms are the same size? No. And so the biggest is the biggest N, so that would be B. All right. Hopefully I've added that to my equation sheet just so that it's easier to do. So we have this general Rn equation, but it's kind of a big thing. But we have the equation Rn, so for whatever level of N, it's just N squared times R over the 1. R of the 1, again, is all of this, which we have been calculated many times, and you can put this on your equation sheet too. So R1 is 0.529 times 10 to the negative 10 meters. So that would be a good addition to your equation sheet. But anyway, so R1 is 0.529, but the other ones would be, so the third excited would be 3 squared times that, so 9 times that, so 9 times bigger. In terms of radius, anyway. All right, on to the next question. Which change will not affect the kinetic energy of the most energetic electrons? Okay, so we have the kinetic energy of photons, Ke max, is in the equation of where we said E of the photon is equal to the binding energy or the work function, or in lab it was called phi, plus Ke max. All right, and so Ke max is E photon minus the binding energy. E photon, remember, is H times F, which is Hc over lambda, stuff like that. Okay, so which will not affect the Ke? Well, changing the frequency is inside of E photon, so that one is not true. It will affect it. Changing the metal affects the binding energy, so that one's not true. changing the brightness of the light. Changing the brightness of the light. So the brightness of the light is how many photons come per second, and that will not change the kinetic energy of each one. That's not in this equation, right? So each one depends on the photon, which depends on the frequency. Brightness will say how many photons come out, how many electrons are set free, but it doesn't say how much energy each electron has. So this is the true. All of them change. No, brightness does not change. So it's C. Okay, according to Du Bois' hypothesis, which of the following statements is applicable to the wavelength of a moving particle? So Du Bois said that lambda was h over p, or p was h over lambda. Momentum was related to the, anyway, he hypothesized that matter, things that have mass, could also have a wavelength like a wave would have. So these are the equations. So which is applicable to the wavelength. So we want it solved in this form. And remember, momentum, P is momentum, is mv. So we can put mv down here. So lambda equals h over mv, or h over p. So lambda directly proportional to speed. No, it's inversely proportional to speed. It's inversely proportional to momentum, yes. It's inversely proportional to mass, yes. Directly proportional to energy. We don't have energy here. But energy, and anyway, it would be like inversely proportional to energy anyway, probably, or not really either, any relation, direct. Anyway, it's not directly proportional. It's not in the equation exactly. Okay, so it looks like B and C there. All right, number 6. The ionization energy of hydrogen atom is, yes, 13.6 eV. What's the energy of the n equals 2 state? Well, we just have the energy equation. E2 is negative 13.6 eV over n squared. N squared. In this case, n is 2, so negative 13.6 eV over 2 squared. 13.6 divided by 4 is negative 3.4 electron volts. Is E2. There we go. The quantum mechanical model of an atom has electrons in a p subshell. What is the maximum number of choices for the quantum number m? So p, the letters tell us about the quantum number L, right? L can be 0, 1, 2, up to n minus 1. Just looking at our equation sheet just to remember. So we have n, L can be up to here, and then m is 0 plus and minus 1 plus and minus 2 up to plus and minus L. And so, well, and then looking at the, I guess I don't really have that. That might be something good to put on your sheet too, but L also has letters. So when L is 0, we call that an S shell. Then when L is 1, we call it a P shell. And then when it's 2, so this is 0, this is 1. When it's 2, we call it a D shell. You can kind of follow along here. D, and then F, and then G, and then H if we get that far. Okay, so if we're talking about a P shell, that's saying, that's the second letter, that's saying that L is equal to 1. All right, what's the maximum number of choices for M? So the rule said M can be 0 up to plus and minus L. So in this case, it's just M is 0 and then plus and minus 1. So M has 3 choices. It can be negative 1, 0, or 1. So this is 3 choices. 3 choices. A. Okay. The ground state configuration for an element is this. What is the atomic number of the element? Okay, so the ground state means it has all the electrons where it is, and so the number of electrons equals the number of protons, and so that's the atomic number. So we just need to count off the electrons. Remember, these these superscripts here tell us how many electrons in each shell. So we've got 2 plus 2 is 4, plus 6 is 10, plus 7 more, so 17 altogether electrons. So 17 is the atomic number. Right? The last shell isn't full, it only has 5 where it could have 6, but there we have it. Alright, next page. Which is true about an alpha particle? So we had some alpha particles in lab. They were just a helium atom that lost its electrons. So any ones that have electrons are not right. Well, okay, all of them. So it's just 2 protons and 2 neutrons. So that's B. Alright. The nucleus of an atom is made up of what? Okay, this is getting pretty basic. Just protons and neutrons. The atomic number of a given element is equivalent to which of the following? Number of protons. Okay. According to the Rutherford model of an atom, most of the volume of an atom is. So remember, Rutherford shot alpha particles at gold foil. And at the time, they kind of thought it was the plum pudding model of atoms, that everything, all the pluses, positives, and minuses were just kind of spread out all over. But he found that most of the alpha particles just went on through. A few bounced straight back, and a few bounced sideways. So he decided that there was mostly free space, and he's the first one that said that the positives were focused in the center, and there's of the atom, and then there was a lot of kind of free space where the electrons were outside. And so most of the volume of the whole atom was empty space. Okay. In contrast to the plum pudding model, Rutherford's model, well, there's a question mark, maybe colon here, was the first to explain atoms emitting frequencies. No. Had a positive charge concentrated in a small region. Yes. Eliminated radiation from accelerating charges. No. No. Alright, so that one is B, like I was just talking about here. Bohr was the first to assume that, so he took Rutherford's model of the planets, the electrons moving in orbits around the planets, but he was the one that was kind of looking at just the energy of the atoms. Yeah, with that, so they could move in kind of a layer or levels without losing any energy or emitting any radiation, giving off energy. So let me see. Yep. Okay, 15. Ionization energy is the amount of energy they require to take an electron from its ground state on an atom. And so ionization, so you make an ion by taking out an electron. So remove it from the atom, B. An electron volt is the amount of blank an electron gains by accelerating through a potential difference of 1 volt. Electron volts are energy, a different kind of energy measured, much, much smaller than joules, the standard measure. The energy of an electron in its ground state of a hydrogen atom is negative 16.3 eV. Alright, we got the E1, negative 13.6. Negative 13.6, that's what I meant to say. EV over 1 squared, so it's negative 13.6. Okay. Which is, anyway, the negative of the binding energy. 18. What is the longest wavelength capable of ionizing hydrogen in its ground state? Longest wavelength capable. Alright, so we want E equals hc over lambda. We're talking about photons of energy. We can use, I don't know if we can use the, yeah, 1240 eV times nanometers divided by lambda equals, and so the energy needed is that 13.6 eV. right? The photon has to give in 13.6 eV so that the hydrogen atom the electron can be pulled all the way out. Okay, and so lambda eV, if we solve this, lambda will be in nanometers because of this unit thing here. So lambda will be 1240, let's just leave the units on there, eV nanometers divided by 13.6 eV. So the EVs go away and we get nanometers. So 1240 divided by 13.6 is 91.2 nanometers. 91. A. What is the de Broglie wavelength of a 0.4 kilogram billiard ball moving with a velocity? So this is going to be very, very small because this is a real mass kind of thing, and so it only really the Broglie wavelengths kind of stuff is useful when we're talking about very tiny things moving very fast. This is a big thing moving kind of fast, but not fast according to electrons. So anyway, it's just kind of an exercise in using the formula. So remember we had lambda for the de Broglie wavelength. Lambda was h over p, which was h over mv. Yes, that's on our equation sheet. That's good. Just double checking here. So here's our de Broglie stuff. All right, and so h is Planck's constant, 6.626 times 10 to the negative 34 joules seconds, joules times seconds, divided by mass. In this case, it's the billiard ball mass, 0.4 kilograms, and velocity is 2,000 meters per second. That should be awful fast for a bowling ball, or for a pool ball. But anyway, lambda is what? 6.626 e negative 34 divided by let's get a parenthesis in here. 0.4 times 2,000. 828 times 10 to the negative 39 meters. Smaller than we can measure, I'm pretty sure. So that's E. All right, that's good for the multiple choice. Let's just double check my answers. So we've got EA, GBBC, looks good. Okay. Moving on to the problems, workshop problems. Consider photons hitting a sample of sodium metal with binding energy, which is also called work function, of 2.2 electron volts. What is the maximum possible speed of a released electron if the wavelength of the light is 500? Okay, so we've got a few steps to do here. We're going to use the E photon equals binding energy or work function plus Ke max. And so we can get Ke max is E photon minus the binding energy, because we know we asked for speed. Speed we know is going to be, or hopefully we can think of it as, remember that it's in kinetic energy, it's related to speed, right? So 1/2 mv squared. So if you get the kinetic energy, then we can get the speed. But we're talking about binding energy and stuff, and this is about the only equation we have with binding energy, so we'll do that first. So Ke max, we also have wavelength instead of E photon, and so we can use the 1240 eV, yeah, we'll go with that, nanometers over lambda minus Be to get Ke max. We're going to have to convert it into joules because this is going to be electron volts, but that's okay. So we got Ke max is going to be 1240 eV times nanometers divided by our wavelength, 500 nanometers. The nanometers are going to cancel. We're going to get EV, but then we got to subtract off the binding energy. This is 2.24 EV. So 1240 divided by 500, and then subtract off 2.24, and we get 0.24. Yep, okay. Is KE max, but we want it in joules, so we can do 1/2 mv squared and get velocity in meters per second, all standard kind of stuff. So 1 EV is 1.602 10 to the negative 19 joules. And so our KE max in joules is 0.24 times 1.602 negative 19. 38 point, we'll just keep one extra sig fig for a minute. 38.45 10 to the negative 21 joules. 21. All right, so we're going to use that is equal to, so KE max is 1/2 mv max squared. So V max takes divide through by 1/2 KE, divide through by 1/2 m, and then take the square root. So we've got KE max over 1/2 m. In this case, that's going to be a square root of 38.45 10 to the negative 21 joules over the 1/2, we'll do 0.5 times mass. We're talking about electrons, so 9.11 10 to the negative 31 kilograms. Kind of running out of room here, but I think it'll work. Square root of 38.45 negative 21 divided by 0.5 times 9.11 e negative 31. Looks like 291 times 10 to the third meters per second equals V max. Let's see if that's what I got last time. Something like that. All right. Somehow I had 290, but we'll go with it. What is the minimum frequency of light that can cause electrons to be emitted from the sodium? Minimum frequency. All right, so we're going to do E photon is equal to binding energy plus KE max. When we want to put in the minimum energy from our photon, we're going to let there be no extra kinetic energy, so all it's going to be is binding energy, so it's going to get out and just going to be stuck sitting there, no speed, just barely got out, and that's how we can figure out the minimum frequency. And so one equation for the photon energy is H times frequency, Planck's constant times the frequency, and if that, then that's equal to the binding energy. But we're going to want this in joules because this is H is in joule seconds, and this is 1 over seconds, and so let's change this to joules. 1 electron volt is 1.602 10 to the negative 19 joules. So the electron volts cancel, we'll end up with joules. (358.8) 10 to the negative 21 joules equals H, Planck's constant, 6.626 10 to the negative 34 joules times seconds times F. So F is 358.8 10 to the negative 21 divided by 6.626 10 to the negative 34. So F is plugging that in, and I get 542 10 to the 12th hertz. 1/2 is hertz. Okay, looks good. If a 1/2 milliwatt laser is used to shine light on the sample, how many electrons are released per second? All right, so this is watts. A watt is a joule per second, so we got 0.5 times 10 to the negative 3 joules every second are sent in. To get each electron, though, each electron has to have a photon. And each photon, did I calculate the energy of a photon in joules? Okay. We're going to have to know the wavelength. We'll assume that we're using the 500 nanometer wavelength, like we're using up here. And so we can get the energy of each photon, which we never did calculate exactly. We just did. So let's go ahead and calculate the energy of a photon of 500 nanometer light. And so E photon is going to be hc over lambda, and let's just do it in regular units so we get joules. So H is 6.626 10 to negative 34 joules times seconds. C is 3 times 10 to the 8th meters per second, so the seconds are gone. And then we will divide by the lambda, which is 500 10 to the negative 9 meters. The meters are gone, and we end up with joules. Yes. Okay, so E photon is 6.626 E negative 34 times 3E8 divided by 500 E negative 9. So the energy of one of these photons is 397.6 10 to the negative 21 joules. Okay, and so that is how much we need for each, how many joules we need for each electron. So let's just divide here by 397.6 times 10 to the negative 21 joules per electron. And so we're going to get, when we divide this, the joules are going to cancel, and we're going to have, this says electron. And so when we divide fractions, we flip over and multiply, so this will be electrons per second is what we'll end up with. Electrons per second. And so let's just put those numbers in. 0.5 E negative 3 divided by 397.6 x times 10 to the negative, lost my 1 there, 21, negative 21. So I get 1.26 times 10 to the 15th electrons per second. How many electrons are released per second? Okay, that should do it. What is the stopping potential for this sodium metal? Remember the stopping potential, if we took the work function is equal to the stopping potential times the charge of an electron, and in electron volts this just goes away, and so then it's just, we can just, basically the value of the binding energy in electron volts is also the voltage. So V equals 2.24 volts, because we got 2.24 electron volts equals V naught times the charge of an electron, so we can think of it as electron charge cancels out. So however you want to look at it, the stopping potential number wise is equal to the binding energy in electron volts. Units are different, but we can get the number that way. Alrighty, 21. Hydrogen atom, if the radius of the electron orbit at the n equal 1 level is 0.529, what is the radius at the n equal 3 level? Okay, so we have our equation. R1 is 0.529 nanometers. I wonder if that's a typo. Because I was thinking it was 0.529 times 10 to the negative 10. Let me look that up a second. I've got my numbers mixed up. .529 times 10 to the negative 10. So this should be times 10 to the negative 10 meters, not negative 9. All right. Yeah, because we're talking about the hydrogen atom. So that's the Bohr radius. Yeah, so let's get the right number in there. So what is the radius of the n equals 3? So we're going to use the equation R sub n is equal to n squared times R1. So it's important to have R1 right. And so in this case, n is 3, so it's going to be 3 squared times this 0.529 times 10 to the negative 10 meters. All right, so 9 times 0.529. So Rn, or R3, R3 is 4.76 times 10 to the negative 10 meters. Okay. If its electron moves from the n equals 3 level to the n equals 1 level, calculate the energy and wavelength of the emitted photon. All right, so we've got, it's up here in the n equals 3 level, and it's going to go down here to the n equals 1, so it's going to lose energy, and so it's going to, that energy will then become a photon that gets emitted. All right, so calculate the energy and wavelength of the photon. So first we'll find the energy of these levels. E3 is negative 13.6 EV over 3 squared, so 13.6 divided by 9 is the negative 1.51 level, and then n equals 1 is a negative 13.6 EV level. And so the amount of energy it gives up is final minus initial, or, well, the change is final minus initial. That's how much it loses. So that's how much the photon gains. Anyway, we want to just take the difference of these two. So let's just do, negative 1.51 EV minus 13.6 EV. So we get the same as 13.6 minus 1.51. Because this is plus, minus a minus makes a plus. And so we have 12.09 EV is how much energy the atom loses, which is what the photon gains, And so, so I guess delta E of the atom is that, and that's going to be E of the photon. When a photon gives energy, then the photon energy equals how much the atom gains. So you just kind of have to look at where the energy is going to see your positive and negative signs, or how delta E of the atom relates to E of the photon. But in this case, it's positive. And so E photon, okay, so energy wavelength of the photon. So E photon, there we go. There's the energy of the photon. Now we want the wavelength. E is hc over lambda, or we can use our little shortcut equation, 1240 eV times nanometer over lambda. Again, this is just hc in special units. And so that is equal to this 12.09 eV. And so lambda is 1240 eV times nanometer over 12.09. I'm probably keeping too many sig figs here. EV. EV's cancel, we get nanometers, so 1240 divided by 12.09. 103 nanometers. Okay? So that's the energy of that's the wavelength of the emitted photon. Double check my calculator work and my math here. 103, yes. Okay. If a 691.9 times 10 to the 12 hertz photon, so this is its frequency, hits an atom in the first excited state, so this is n equals 2. Again, it's the hydrogen atom. This is all about hydrogen atom. What state will the electron move to? Okay, so it's going to be in a lower state, in the n equals 2 state now, and it gets more energy from the photon, so it's going to go up to n equals a higher number, right? So we'll calculate how much energy it has, and then we will see what level that ends up being. Okay, so it starts in the n equal 2, so it starts in the 2 level, which is negative 13.6 eV over 2 squared, right? So 13.6 divided by 4, I think I've done this before. Negative 3.4 EV level is what it has. So it starts at E2, negative 3.4 EV, and then it's going to gain from the photon, HF. Okay, let's calculate E of the photon is HF, which is 6.626 10 to negative 34 joule seconds, times F, which is 691.9 times 10 to the 12th hertz, which are 1 over seconds, so the seconds are gone. And we get joules, but we want it to be an EV. So let's go ahead and multiply this by 1 EV is 1.602 10 to the negative 19 joules. So the joules cancel. Get all that together, so we get E of the photon in electron volts. So 6.626 E negative 34 times 691.9 E 12 divided by, it's on the bottom, 1.6602 E negative 19. Oh, I had to get 2.86 electron volts. Okay, so this is going to be plus E of the photon, so it's going to start out at negative. So we're going to put this up here. I got crisscrossing things going on here. So we got negative 3.4 EV plus 2.86 EV. So the new level, our new energy is negative 3.4 plus 2.86 negative 0.54 EV is the new level, is E something, we don't know what it is. And so we're going to use the equation that E sub n is negative 13.6 over n squared EV. That has to be this negative 5.4 number, negative 0.54 number. Negative 0.54. So solving this says n squared equals, the negative and negative cancel, so it's going to be 13.6 over 0.54. So n squared equals 13.6 divided by 0.54. Well, sig figs are getting kind of, let's just go with the 25. So n equals 5, because n has to be a whole number. So we got rounding issues, but n equals 5. So it moves to the n equals 5 state. Okay, good. Which is higher, like we expected, moving up to a higher shell. What is the maximum wavelength of a photon that can release an electron from the n equals 3 state? N equals 3 state. Release it from the n equals 3 state. So that means get it all the way out. And so let's find the energy at the n equals 3 state and then find the energy of a photon that matches that. So 3 state, negative 13.6 over 3 squared. EV 13.6 divided by 9. That's the negative 1.51 EV. And so we want wavelength, so let's just use, we're going to make that be E photon, or at least positive of that be E photon. And so, getting messy here. So we want E photon to be positive, that's a 1.51 EV to pull it out. Alright, add this to that, we get 0, so it's free. It has 0 energy, so it's the minimum. Alright, so that equals, we can use our 1240 EV, or HC over lambda, but 1240 EV nanometers over lambda. So lambda equals 1240 EV nanometers over 1.51 EV. The EVs cancel, we get nanometers. 1240 divided by 1.51. 821 nanometers. All right. Good. Keep on moving. What is a ground state electron configuration? The ground state for electron configuration for chlorine is this. List the quantum numbers for the 6 electrons in the outer subshell, this 3p6 shell. All right, so when we're looking at something like this, the 3 is n, right? The quantum numbers are n, l, m, and s, right? So n is the first number, the primary or the principal quantum number. P, the letters tell us L. L goes 0, 1, 2. The first one is S, and the second one is P. So L is 1 for a P level. And then this is saying there are 6 electrons in that shell. All right, so that's what it's saying. What are the 6 quantum numbers? So we know they're all going to have n equals 3. And L equals 1. And then, so what are M and S? All the different M and S combinations. And there should be 6 different M and S combinations. So let's do 3, 1. There are going to be 3, 1. Let's just write them all out. 1, 2, 3, 4, 5, 6 choices. Okay. So this is N, L. And so now when L is equal to 1, what can M be? Remember our rules. when L is equal to 1, M can be 0 up to plus and minus L, right? So M can just be 0, plus 1, minus 1. Yep, because L is 1. All right, so let's do some M's here. So M, but then for each M, we're going to have two S's. Remember, S is going to be plus a half and minus a half. All right, so for each M, we're going to have two choices for S. So we're going to start with M is -1 twice, 0 twice, 1 twice, right? And so then the S is negative a half, positive a half, whichever order you want to go, negative a half, plus a half, negative 1/2, plus 1/2. All right, list the quantum numbers. Okay, so this is the list for the 6 cases. 3, 1, -1, negative a half, 3, 1, -1, 1/2. So there's our list of our 4 quantum numbers for the 6 different electrons in that 3p6 shell. Okay. How many electrons are possible in an n equal 3 shell? Show your work and your proof. So the whole n equals 3 shell. So when n equals 3, then L can be 0, 1, and 2, because L goes from 0 to n minus 1. And then, let's see, how can we do this? Is there an easy way to write this out? I don't know. So for L equals 0, we can have, what can M do? M can only be 0, right? And then S can be 1/2 and minus a half, right? So that gives us just 2 electrons from this combination, right? N is equal to 3 for everything, right? So that's the L equals 0 case. We only got 2 electrons from that, and that makes sense because the L equals 0 is an S shell. It can only have 2 electrons. All right, L equals 1 says M equals -1 or 0 or 1, and then for -1 we've got S equals a half or negative a half. 0 is a half, negative a half. For the 1, 1/2 S and negative a half. So for this level we got 2, 4, 6. So we get 6 electrons when L equals 1, right? This is an S, this is a P, right? And then finally we can also get L equals, that was for L equals 1. So altogether so far we have 8. And then when L equals 2, so this is a D subshell. Now M can be -2, -1, 0, 1, 2. And for each one of these, we're going to have a 1/2 and a negative a half. 1/2, negative a half. So forth. I'm getting tired of writing 1/2, and I'm getting out of room. But each one of these is going to have a half and a negative a half for their S values. And so we got 2, 4, 6, 8, 10. The D shell can have up to 10 electrons. When it's full, it has 10 electrons. All right, so for everything, that's the biggest one. And so for all the different shells, S, P, and D, we can have 18 electrons. So 18 electrons in an n equals 3 shell, in the whole shell. Okay, write the electron configuration for titanium, atomic number 22. Okay, so we're gonna, for this, we're gonna want to go back to our equation sheet here that gives us the order of things so we can fill in the shells in order. So we're going to start with, so this gives the order that all of them will fill in at. So we got a 1s. It's going to be, s's can go to the 2 level. I mean, have 2 electrons. So we got 2 so far. We're going to 22. And then we're going to have a 2s, 2. It's going to be all full. Then we have 4. 2p. P's can have 6. So far now we've got 10. We still need 12 more. So we'll keep going. 3s. S's can have 2. So now we got 10. We got 12. Now we need 3p is the next level. If we go to 6, we have 10 plus 8, so that's 18. We still need 4 more. What's after the 3p is a 4s. So that's 2. So now we had 8. So we got 20. 4 plus 6 is 10. 4 plus 6 is 10. So that's 20. So now we've got, after the 4s, we get a 3d. How many does the D level can hold? What did we just did that. SPD, a D level can hold 10, but we don't need 10. We only need 2 more because we got 10, 20. So we just put a 2 in there. So we got 22 electrons. 10, 22. Yep. So we followed the order for filling them in and went up to the number, the atomic number for the electrons. Okay, how many electrons are in the outermost subshell of a titanium atom? So the subshells are just these layers. So the whole shell would be like the N level, and so you'd have a whole bunch like we had here. But now for a subshell, it's just one of the L letters, so that's D. And so this one only has 2 electrons. What is the value of L for this subshell? So it's a D shell, so that means L equals, it goes SPD 0, 1, 2, so L equals 2. Okay, looking good. One more page. What is the de Broglie wavelength for an electron traveling 10% the speed of light? Okay, so the de Broglie wavelength is h over momentum, where h is Planck's constant. And momentum is also mv if we're talking about something. Usually de Broglie wavelength is thinking of matter having wavelengths, so it has mass. So it's going to be mass of an electron. 10% of the speed of light, so v equals 0.10 times the speed of light, which is 3 times 10 to the 8th meters per second. So v in this case is 0.3 times 10 to the 8th meters per second. Just plug it in. So lambda equals h 6.626 10 to the negative 34 joules times seconds. ME 9.11 10 to the negative 31 kilograms. And V 0.3 10 to the 8th meters per second. Okay. Yeah, this is matter, electrons, so yeah, this is going to be a very small wavelength, 24.2 10 to the negative 12 meters. Lambda. What is the de Broglie wavelength for an electron with kinetic energy of 14 electron volts? Okay, so we've got Ke. So we're going to use the same equation. We need to find the velocity, so we're going to use kinetic energy as 1/2 mv squared. And so we're going to say that then the velocity, divide through by 1/2 m, take the square root. Velocity is going to be the square root of Ke divided by 1/2 m. But we need the kinetic energy to be in joules, not electron volts. So Ke 14 eV times 1 eV divided by, anyway, 1 eV is 1.602, 10 to the negative 19 joules. So the kinetic energy in this case is 14 times 1.602 e negative 19. 2.243, I guess, keep an extra sig fig for a moment, times 10 to the negative 18 joules. Okay, so the velocity is the square root, put that in there, 2.243, 10 to the negative 18 joules divided by 1/2. This is, we're talking an electron, so mass of an electron, 9.11 times 10 to the negative 31 kilograms. Get our equation here, square root, 2.243 e negative 18 divided by, put in parentheses so we don't get messed up, 0.5 times 9.11 e negative 31. 2.22 times 10 to the 6th meters per second. Oh, hold on, that's not the final answer, that's just velocity. Okay, and so we want the wavelength then is h over mv, 6.626, 10 to the negative 34 over 9.11, 10 to the negative 31 kilograms, and this new velocity, 2.22 into the 6 meters per second. $328 times 10 to the negative 12 meters is this lambda. Alright, I'll have to go with it because I forgot to calculate that part last time. Just double check my calculator. Looks good. Okay, double check me on that, just to make sure. Okay, so if an electron has a de Broglie wavelength of this, what is its speed? Okay, so we're going to be going kind of backwards. Use this equation again. So we've got lambda equals h me v, second electron, yes. And so we're looking for speed. So v, rearrange this, multiply through both sides by v and divide both sides by lambda. We will end up with, divide both sides by lambda, h over me lambda is equal to v. And so our velocity is h, 6.626, 10 to the negative 34 joule seconds, divided by mass of electron, 911, 10 to the negative 31 kilograms, and the lambda, 80.9 times 10 to the negative 12 meters. So our velocity is 8.99 times 10 to the 6th meters per second. Okay. Looks good. And that's the test.